Welcome to the session on closed-loop engineering of ADAS and autonomous vehicle technology from chip to city. My name is Mathieu Worm. I'm a Director Autonomous Vehicles for the Simulation and Test Solutions Group at Siemens. In this session, we look at the automotive industry and the transition or the disruption that this industry is in. We'll discuss the closed-loop engineering process that is required to be part of that transition and to cope with the challenges of that transition. And I'll dive a bit deeper into the different phases of that closed-loop engineering process, ending up with a picture of how that process fits into the larger model-based systems engineering technology that we as Siemens bring to the industry. So, what is happening in the world? We develop autonomous vehicles that are a solution in itself, but actually are only a component in a much larger problem. And that problem is urban mobility. We see cars in every city standing still, being parked, with people spending time looking for parking places, standing in traffic jams. And autonomous vehicles are part of fixing that urban mobility challenge. And the industry recognizes that. It has a massive impact on how we look at vehicles. And for example, Satya Nadella from Microsoft, in a discussion with the former CEO of Daimler, recognized that cars are no longer cars, but actually become computers on wheels. It leads to situations where technology companies are in a position to order 20,000 vehicles at a traditional car OEM, and with that dictating the pricing of vehicles. We see companies like VW and Ford, competitors for the past 100 years, finding ways to jointly invest in autonomous vehicle technology. We see NVIDIA and Mercedes partnering up, where NVIDIA is the first company to be mentioned in the announcement at Forbes, and where Forbes also highlights the importance of the new business models that we'll see with electric, connected, autonomous and shared mobility. Hyundai and Aptiv put up a joint venture now called Motional, deploying self-driving robotaxis in US, Korean and Singapore city landscapes. So what impact does that have? If we look at autonomous vehicles as computers on wheels, it is a control system that takes in sensor data, that fuses that sensor data into meaningful data to determine a path and to derive actuator outputs. These actuator outputs lead to vehicle behavior and to interaction with the environment and other traffic agents. And soon we will also see direct information coming into that control system from vehicle to vehicle communication and vehicle to infrastructure communication. We as Siemens take a perspective, what we call from chip to city, meaning that we support digitalization at the level of the chip and the core electronics. We model and digitize system level solutions, sensor simulation, controls for perception, controls for planning. We model and virtualize the vehicle, chassis systems, powertrain systems, entire vehicle configurations, including the sensor integration part. And finally, we put these simulated vehicles in a simulated environment. So we build a digital twin from chip to city, and we support and enable digital continuity throughout that supply chain, from the chip makers to the electronics companies, into the traditional tier 1 suppliers and the OEMs, up to vehicle levels where cars become part of a system of systems. So how we do that is then depicted on the following slides. So starting off with the chip level offering, we bring the capability to model chips in simulation and emulation technologies and couple these virtual chips into a realistic testing environment for automotive use cases. That simulation environment at the level of the vehicle and the systems is, for example, being used by Hyundai Mobis to build up an integrated engineering process of data collection with engineering fleets, as well as massive virtual validation and verification cycles. Then, if these cars become part of a city landscape, it is mainly through the connection into Siemens Mobility that the Siemens Digital Industries software portfolio is being used to test vehicles in a larger city context. So on the bottom right movie, you can see how the Setran testbed in Singapore has been equipped with vehicle-to-infrastructure communication technology from Siemens Mobility, and how we build a digital twin of that test environment to insert virtual pedestrians for which the car can stop. And in the timeline depicted on this slide, you can see that we work towards a situation in 2022 where there is coordinated traffic systems that require real-time simulation. So there is an executable digital twin running in the background to optimize the entire mobility system. So with that new reality of computers on wheels also comes the need for a new development process, where the traditional automotive industry works along the lines of a V-cycle, where at the end of that V-cycle, the product is done and being sold to an individual buyer. We move into a new reality where when the product is done, it starts to collect data in real life. With the Simcenter portfolio for the development of autonomous vehicles, we support this closed loop engineering process, meaning that we enable the data collection of raw sensor data on real roads, capturing massive amounts of camera, radar, LiDAR, CAN, GNSS data in a synchronized manner. We bring the capability to process that data, to analyze and diagnose that recorded data for either the creation of data sets for training of neural networks or for the identification of critical scenarios for validation and verification. Then we support the design and exploration phase with sensor simulation capabilities at the level of the sensor, at the level of the sensor within the vehicle context, and also with sensor models on vehicles that drive through the environment. And then finally, when we have supported the design of these vehicles, we bring the capability for both virtual as well as physical validation and verification. Starting off with pure virtual, massive validation and verification through real-time testing, hardware in the loop, software in the loop, vehicle and driver in the loop, up to the point where the vehicle is ready to be tested on proving grounds and in actual traffic. So if I move through that loop and through the phases of that loop and illustrate that a bit more, we start off with the capturing and monitoring stage, where we deliver onboard data acquisition systems with massive storage capabilities to capture raw data. So terabytes of data that at the end of the day can be uploaded into the cloud to become available to the engineering community. Part of that solution is also the real-time playback for hardware in the loop and software in the loop setups. If I have collected data, it's not straightforward to use that data. So a lot of the services that we bring today is to come from recorded data to what we call meaningful data, and to ensure that you can use that data in virtual environments. So the transition of recorded data into virtual data is a very important step. And in that step, we rely strongly on standards like the Open Scenario, Open Drive standards. But also what we bring there is a capability for what we call design of experiment, identification of critical scenarios that are not seen on the real road. Because the key challenge of verification of autonomous vehicles is to test vehicles against the critical scenarios. And a lot of critical scenarios come out of recordings on the real road, but there will never be a situation where all critical scenarios can be captured with data recording systems. And that's where design space exploration techniques come into play, where we start off from known scenarios, but generate unseen, unknown critical scenarios in line with the standard for SOTIF, the safety of the intended function, to grow the scenario space for testing self-driving vehicles beyond the situations that are known. So having recorded data, having analyzed and diagnosed this recorded data, we move into the stage of design and exploration. Starting off from functional requirements and functional architectures, deriving domain-specific architectures for the electric systems, for the network design, for your embedded software design. We bring solutions to the industry to design these systems and to integrate these systems in a specific vehicle context. That also applies for sensor technology, assessing the impact of a position and location of a sensor in a headlamp or behind a windscreen or behind a bumper, and what that does to the quality of the signal of the camera, the LiDAR, the radar, are capabilities that we bring to our customers. And an example there is a startup in the LiDAR domain, Xenomatics, developing pure solid-state LiDAR systems. We worked together with this company on the validation of our physics-based LiDAR model, putting Xenomatics in a position to virtually design their sensor system and, for example, also their perception algorithms. So we generate here a point cloud that is similar as the point cloud that they can develop by driving around with that vehicle. Having a good model of your vehicle and a good model of your sensors, and having that digital twin of the world, these test scenarios that you want to use for the validation and verification of your systems, puts you in a position to start running big amounts of simulations. And the challenge there is to orchestrate that process, to be able to automate a lot of steps in that process. And that's what we bring to the table with Simcenter Prescan 360. So having the capabilities to start off with a vehicle model and a basic set of scenarios, generating many variants of these scenarios with different weather conditions, with different road friction levels, with different speeds of the objects in the environment, with different qualities, signals of the sensors, so taking into account sensitivity of sensors. We can run all these different scenarios in a cloud or cluster environment and also automatically post-process these results. So generating insight that shows which scenarios did not result in any dangerous situation, but also identifying the situations where there were actually false positives of the systems, and obviously also identifying the domains where the safety system was not capable of preventing an accident, and then bringing insight into the severity of these accidents. Bringing that insight puts you in a position to start a falsification approach, meaning that you can actively search for the scenarios that make your controller fail. And that puts you in a position to optimize your vehicle against relevant critical scenarios, rather than testing your system for a large number of miles or a large number of scenarios, not knowing if you have really found the critical domains of your system. So we simulate the vehicle dynamics, chassis systems, powertrain systems. We can put these detailed vehicle dynamics behaviors in a virtual environment and, for example, develop autonomous valet parking systems where also tire dynamics are taken into account. So low speed tire dynamics are very complex behaviors. Not taking these into account can lead to a controller design that is not functioning in real life as you would expect it to behave. On the right side, you can see a movie that illustrates the fact that we go beyond the automotive industry when it comes to supporting the development of autonomous systems in the agricultural industry, in the heavy equipment industry, but also in the urban air mobility solutions, where we see a big trend these days for the development of drone kind of robo-taxis that need to fly at relatively low heights, need to stay away from objects, unexpected objects, so more extended sensor systems are being used, and we're able to model not only the dynamics of these flying objects, but also the sensor systems of these vehicles. Doing an assessment of the safety performance of the different systems is not straightforward. There is static metrics like time to collision that you can measure. But if you would like to develop a system that is not overly conservative, so that keeps driving in situations where it can drive and that can speed up to comfortable velocities. You need much more smart metrics than these static metrics. In this context, we work together with IVEX that has developed the safety assessment tool that continuously calculates a safety envelope around the vehicles, so 20 times per second reassessing the required safety distance towards other objects, and we coupled that metric into what I just presented called Simcenter Prescan 360 into that massive validation verification environment to automatically bring insight in the domains where the vehicle has most difficulties. And for example, finding out that under specific weather conditions or specific lighting conditions, your vehicle is most challenged by the system to behave safely. Then I'd like to close off with fusing that infinity loop picture, that closed loop engineering picture, into the larger context of the Siemens accelerator portfolio. So where the accelerator portfolio supports model-based systems engineering, starting off with requirements, starting off with a functional architecture, bringing the capability to digest requirements and architectures into domain-specific architectures and requirements that can be given to the individual teams that develop the electronic systems, the network systems, the software systems, but also the mechanical parts and even the core electronics and system-on-chip solutions. What we bring with Simcenter is an environment to do design optimization, to do an analysis on the different performances and also multi-attribute performance verification. But probably key in the domain of autonomous vehicles is that we bring the capability to collect data, to digest collected data, to support the design of perception systems and integrate these perception systems into a vehicle context, and then to run first massive validation and verification cycles, and finally move to the point where you can put the vehicle on the road and start to collect again data with these developed cars. So that's what we call closed loop development for ADAS and AV technology from chip to city. And with that, I'd like to thank you for your attention, and I wish you a very good day. Thank you.